In an earlier lesson, we talked about strong-strong titrations. Here, we're going to discuss weak-strong titrations. Now, let's look at the curve on the right side of this screen. Previously, we looked at a pH curve for a strong-strong titration, and that curve differed from this one in this way. If you follow my laser pointer here, in a strong-strong titration, this started out and the curve was fairly flat but with a slight slope, and then all of a sudden right about here it just went whoop vertical, and then from that point on it looked pretty much like what we have on this graph here. For a weak strong titration, we have a slightly different shape. We have this kind of gradual changing of pH, and then we have a vertical region, but it's shorter, and then we have the elongated, slightly sloped region, which is the same essentially in both strong-strong and strong-weak titrations. But this region here is a different shape in a weak-strong titration than in a strong-strong titration. And that's because this region right here is sometimes called the buffer zone or the buffering region, because when we have a weak-strong titration, as the reaction is going on, we're actually producing something that affects the pH of the solution. So let's look on the left side of the screen here. The equivalence point is when, say, 50 mils of 0.1 molar NaOH, that's a strong base, have been added to 50 mils of 0.1 molar acetic acid, that's a weak acid. But the pH is greater than 7 at that point because the acetate ion that's generated by the reaction acts as a weak base. In a strong-strong titration, the pH will be equal to 7 at the equivalence point. In a weak-strong titration, specifically here in the case of a weak acid strong base, the pH is going to be more basic. It's going to be greater than 7 at the equivalence point, because look what happens. You see this hydroxide ion? I'm circling it here. It's in the middle of the screen, slightly to the left. That hydroxide ion is going to do what? It's going to rip protons off right there, off of that acetic acid molecule. And what's going to be left of that acetic acid molecule when that proton has been ripped off? Isn't it, down here in the lower left corner, this acetate ion? And what does that do in solution? Doesn't it try to gain protons? So it acts as a weak base, which means the equivalence point will be at a place where the pH is greater than 7. Titration curves for polyprotic acids, like carbonic acid, look something like this. They have 2 equivalence points. We're not going to go into any more detail on polyprotic acids. So let's try a problem here. We're going to calculate the pH at the equivalence point if 40 mils of 0.025 molar benzoic acid, which is a weak acid, are titrated with some strong base. But first, let's review. When we add a strong to either a weak or a buffer, and that's what we're doing here, we first need to calculate the concentrations after the reaction using stoichiometry, and then calculate the equilibrium concentrations using Ka or Kb. We need to do the reaction first using moles, and then we need to do an equilibrium calculation using molarity. Here we go. There's our benzoic acid. We've also got hydroxide ion. These are the 2 species that are going to react. Before the reaction, we have 0.001 moles of benzoic acid. I'm sorry I don't have room on this slide to show all of the work, but I will at least say what's happening, so hopefully you can understand. Whenever we do the reaction, we need to take into account moles. Molarity, if you look in the upper left corner of the screen, molarity is moles divided by if you look in the upper right, liters. So what I've done here to calculate moles of benzoic acid is I've taken molarity, 0.025, times the number of liters, which 40 milliliters is 0.04 liters. Molarity times liters gives me moles. So that's where that number came from. How many moles of hydroxide ion do we need in this reaction? The answer is 0.001 moles, because at the equivalence point we have to add equal numbers of moles of H, which is hanging on the end of the benzoic acid molecules, and OH. This number here that I'm circling with my laser pointer, we calculated. This number here, we know must be the same as the first number we calculated. To get 0.001 moles of OH, that required 0.02 liters, because the concentration of the base was 0.05 molar. So to get 0.001 moles of OH, we had to add in 0.02 liters of the base. So now the total volume is going to be the 0.02 liters of base that we added, plus, in the upper right corner, 0.04 liters of acid. Okay, so that's where our total volume now comes out to be 0.06, because we've added the acid volume and the base volume together. So now these two are going to react. The OH is going to rip off H's from the benzoic acid, which means we will have no benzoic acid molecules left at the end, and we'll have no free hydroxide ions left at the end. We'll have water as one product, and isn't the other product going to be the benzoate ion, which is what is produced when the H has been ripped off? Initially we had none of that. Afterwards, don't we have 0.001 moles of it? That's the end of the reaction. Now we need to do an equilibrium calculation. We've taken moles of benzoate ion and I've converted it into molarity by dividing by the volume, which is 0.06 liters. 0.001 divided by 0.06 gives me this concentration of the benzoate ion, which is what we need if we're going to do an equilibrium calculation. This benzoate ion is going to act as a weak base, so we're going to react it with water to form benzoic acid again and some hydroxide ion. We need the Kb for this benzoate ion, which is not given, but the Ka in the upper right corner of the screen, the Ka for benzoic acid is given, and from it we can calculate the Kb of the benzoate ion, because remember that the product of Ka and the Kb of the conjugate of a conjugate acid-base pair is 1 times 10 to the negative 14th. Well, again, sorry I don't have room on the screen to show all this, but now that we have Kb, we can go products, which is going to be x squared, divided by reactants, which is 0.0167 minus x. We would use the shortcut. We would calculate x, which turns out to be the OH ion concentration. Once you find the OH ion concentration, you can calculate POH, and then you can calculate pH. If you do that, it turns out to be 8.21. There is a good deal of thought that goes into one of these problems, but we can see, if we do these calculations, that at the equivalence point, when you mix equivalent amounts, or stoichiometric amounts, that's another term for it, of weak acid and strong base, the pH at the equivalence point is slightly basic. And that's because the conjugate base of the weak acid acts as a weak base, pushing that pH slightly higher than 7.